This video covers Section 3 of Chapter 8, where we'll calculate and interpret confidence intervals for a single population proportion and also determine the required sample size for estimating a population proportion. This is really the same idea and process that we used in Sections 1 and 2 of this chapter. So we'll calculate an interval estimate. This interval estimate will be an estimate of the population proportion, and we'll do that using the sample proportion and some allowance for uncertainty. Remember in Chapter 7, the sample proportion is approximately normally distributed if the sample size is large enough, and the standard deviation, or standard error, is calculated using this formula below, square root of pi times 1 minus pi divided by n. Since we do not know the true population proportion, we will use an estimate based on sample data, and that standard error will be the square root of our sample proportion times 1 minus our sample proportion divided by n. This confidence interval formula should look familiar to you. Our sample statistic goes on the left. This was x bar in our previous section. Now it's the sample proportion, plus or minus a critical value. Assuming that our sample size is large enough to assume normally distributed, this will be a z critical value. And then we multiply by the standard error. So let's look at an example. Suppose we've collected a random sample of 100 people that shows that 25 are left-handed. Let's form a 95% confidence interval for the true proportion of people that are left-handed. Our sample proportion, or P, is 25 out of 100, or 0.25. So 25% of the people in our sample are left-handed. Our standard error is the square root of 0.25 times 0.75 divided by 100. That turns out to be 0.0433. And we've got our formula here. Let's plug in the pieces that we know. So P is 0.25. We've got a 95% confidence level, so our z critical value is 1.96. We plug our standard error in where the square root stuff is there. If we multiply and simplify this, we find the boundaries of our confidence interval are 0.1651 and 0.3349. So let's interpret that. We are 95% confident that the true percentage of left-handers in the population is between 16.51% and 33.49%. We know that this range may or may not contain the true population proportion, but we also know 95% of the intervals formed in this manner will contain the true population proportion. So we're fairly confident, 95% confident, that the true proportion is in between these two numbers. To speak about the width of the confidence interval, we're really focusing on the margin of error. The things that make this margin of error bigger make the confidence interval wider. So if we increase the confidence level, that gives us a bigger z critical, and it makes the margin of error bigger, so it increases the width of the confidence interval. To be more certain that our interval contains the true population parameter, we need to make that confidence interval wider. If we increase our sample size, that will reduce the width of the confidence interval. Making n bigger makes this fraction smaller, and so the entire margin of error will be smaller and the confidence interval will be narrower. Based on our example in the last slide, if the sample size is doubled to 100, and suppose that 50 of those people are left-handed, the interval is still centered at 0.25. But instead of being this wider interval from 0.1651 to 0.3349, the interval becomes 0.19 to 0.31. That interval shrinks. We get a more accurate prediction without having to change our confidence level. This reinforces the idea that increasing the sample size, when cost-effective to do so, is a good idea, because increasing the sample size reduces the width of our confidence interval. We get a more accurate prediction of our true population parameter. Remember in 8.2 we talked about three competing objectives: having a high level of confidence, a low margin of error, and a smaller sample size. We want to find the required sample size that meets our margin of error goal and our confidence level goal at the same time. So this is doing the same thing that we did in 8.2, but for the population proportion. So we've got the margin of error formula at the top. By solving for n, we get n equals the critical value squared, the population proportion times 1 minus that population proportion, divided by our margin of error. That margin of error will be in percentage units. Now if we don't know our true population proportion, which we likely won't, then we can estimate that with a pilot sample. If we're unable to take a pilot sample, then we can conservatively use the population proportion of 0.5. 0.5 gives us the worst possible variation, so it will give us the largest possible sample size, given some level of confidence and some given margin of error. So let's walk through an example of this. How large a sample would be necessary to estimate the true proportion of defectives in a large population within 3%? Notice that's our margin of error. We want to be within 3% with a 95% confidence. Assume in this case that we did collect a pilot sample and that pilot sample yields a sample proportion of 0.12. So n equals our critical value squared. If it's a 95% confidence level, our z critical value is 1.96, so we square that. We don't have the population proportion, but we have this estimate, 0.12. So 0.12 times 1 minus 0.12. Our margin of error is within 3%, or 0.03. So we put 0.03 in the denominator and we square that. When we simplify this, we get 450.74. So we should use a sample size of 451 items.